Good morning to all. Today we will talk about, we started in the last class talking about the memory system, and we stop at this point here, that is the direct mapping. Okay. So, I will start from this slide here. So, in case of, as I said, what is the need of the mapping, as you see here, the size of the cache memory is much smaller than the size of the main memory, and as you know that data needs to be brought from the main memory to the cache memory and from cache memory to processor. Okay. So, therefore, very likely and the speed of the cache memory is much slower than the main memory. So, computer expect that almost all data should be available as soon as possible. So, therefore, we need to use some mapping scheme, because size of the cache memory is much smaller than the main memory. So, we will be talking about direct mapping, and I will tell you with one simple example here. Say, let us say we have a cache memory here, it can hold 100 words, and we have a large main memory which can hold 1000 words or byte, whatever you can say, and then main memory is divided into a number of blocks, fixed partition. So, each partition consists of 10 bytes or words. So, therefore, we will have, this is block number 0, block number 1, block number 2, and so on. So, then how many blocks we will have in the main memory? So, we will have last block is 99. So, we will have total, as you can see, 10,000 divided by 10. So, we will have total 100 blocks starting with 0 to 99. Similarly, this cache memory is also divided into a number of blocks, as I said, to not to be confused with the block in the main memory, and cache memory generally that separate name is given. So, that is something called cache line. So, size of the cache line and the block size is same, and because here we have the 100 word. So, the number of cache line will be 100 divided by 10. So, we will have the 10 cache line. Okay. So, now in case of the direct mapping, so if we use the direct mapping, so a number of sorry, it is not number, the cache line I is j modulo m. What is m? J is nothing but the block number and m is the number of cache line. Okay. So, therefore, see here we have a block 0, 1, 2, 3, 4, so on up to 99. Okay. So, let us say, as I said, the CPU generates the address, processor basically generates address. Let us say it generates some address 779. Okay. So, that means processor wants the word which is located at the address 779. Now, what is done is, as you know that 779 actually exists in the block number 77. Okay. So, therefore, where it should be mapped this 77. So, now you perform 77 modulo 10. So, then answer is 7. So, therefore, that block 77 block must be placed in the cache line 0, 1, 2, 3 to 10. So, it must be placed in the 7th block. Let us say 7th block is this one. Okay. Now, question is, so let us say 671, this is different address, another address I said is 779, then maybe another address 872. So, then what will be the corresponding mapping for this address? So, here is block is 67. So, 67 modulo 10. So, then the cache line will be 7 here, here is 77. So, then 77 modulo 10, again cache line will be 7. So, 87. So, again cache line will be 7. So, therefore, 67, 77, 87, these all block will be mapped to the single cache line into the direct mapping. So, maybe I can summarize here. So, let us say block number 7, block number 17, block number 27, block number 37, block number 47, 57, block number 67, 77, 87, and then 97, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This all 10 block will be mapped to the cache line 7. Now, say suppose you have a cache memory and this is cache line 7. As you see, this 10 block of the main memory, 10 blocks of the main memory will be mapped to this cache line. So, now let us say you got the address, let us say 172. CPU wants to access the word which is located into 172. So, as you see, this is the block 17. So, it will be mapped to the 7. So, 170. So, 17 blocks will be mapped to 7. In the next time, I want the 275, this is CPU generate that immediately 275. So, then what will be the block? 27 block, it will also map to the 7 as you can see here. So, then 27 also will be mapped. Similarly, 10 different blocks of the main memory can be mapped to the same single cache line. Now, question, how do you understand whether these data is coming from the block 17 or block 27 or so on? It should be from any one of the 10 blocks. You cannot put 10 blocks together. So, then data will be lost. So, only one block can accommodate, that is 7, cache line can accommodate only the one block at a time. But you need to know that it is coming from the which block of the main memory. Let us say here already that block data was from the block 227, some data is available, but CPU wants to generate, CPU generate the address 172 and that should come from the block 17, but it is not the block 17. So, therefore, so within this cache line there should be some identifier that should identify whether this particular block is coming from the main memory which block. So, therefore, there should be another parameter is called tag. So, that indicates the block number. So, say 27. So, now CPU generated the address 172 and it is located into the 17 block. So, it will match with 27 and 17. So, it will realize, so it is not the 17 block. So, it is 27. So, there will be cache miss, data is not in the cache memory. So, therefore, what we need to do to identify in the direct mapping, we have 3 part. So, one is, see, I said the block size, within the block size there are 10 blocks, sorry 10 words. So, we need to specify the particular word, that in this example say 172. So, actually it wants the second block, similarly this wants the 5th block. So, therefore, to identify that which word within a block, so we should spend a time, we spend a few bits for that. So, because there are only 0, 1, 2, 3, we are working on decimal and then 9 words. So, it will spend only 1 word for that to identify whether it is 0 or 1. So, if it is 2 digit, then we need to identify the, it should be 2 bits. Okay. And next is cache line, whether this block either 27 or 7 is mapped to which cache line. So, this bit indicate the cache line. So, how many blocks are there in the main memory? There are 10 blocks. To identify any one of the block in decimal system, I need only 1 digit. So, therefore, cache line will be 1 digit. Okay. And what next? So, word is 1, cache line is 1, and then what is the total length here? What is the memory size? That is 0, 0, 0. Okay. So, up to 999. Okay. So, next it should specify that this data is coming from the which block. So, data is coming from the which block. So, for that there should be 2, because see block number is starting from 00 to 99. So, at least 2 digit is required to identify which block. So, this is something called tag. So, in earlier example, as I said, there should be tag to identify the which block. Okay. So, therefore, tag should be 2, cache should be 1 and this should be 1. This is actually, as you can see, there are 3 digits. So, it cannot be 2 here. So, it should be 1 here. So, tag should be 1. Why? So, let us say if I CPU wants to generate that, CPU generated that let us say 778. Okay. So, these 3 bits it can generate, it will generate only 3 bits, because memory size is byte is from 00 to 000 to 999. So, this address will be divided into 3 part. One will be what will indicate the word location within the block, next will indicate the block this entirely this block number in the main memory, but this 7 indicates that this is the cache line and rest is indicating, this is indicating is like tag number. This is, let us say if you have a 77, another is like 87. Okay. So, this one and this one is different. See, in this example, let us say 0, 7, 1, 7, 2, 7, 3, 7, 4, 7, 6, 7 all 10, only difference in the single digit, in the second digit, not in the first digit. That first digit is nothing but most least significant digit, sorry, least significant is nothing but the cache line, and most significant digit of the block number is nothing but the tag. So, therefore, this will be 111. So, let us say this address is 778. So, this should be 7, this should be 7 and this should be 8. So, let us take one more example here with the same framework, and then we will go with some example which is quite applicable in computer organization. Let us say CPU generated the address, let us say 981, that means 98 blocks, and it should be mapped to the cache line 8. How do you identify? From the bit position only we can identify. So, this is the word, first word, this is the cache line and this is the tag. So, then main memory address in case of the direct mapping will be divided into 3 part. One is called the word, this is something called cache line, another is called tag. So, tag will tell you whether this block is coming from the desired block or it is from the other block. Okay. Now, we will show few example in case of the direct mapping. So, we are talking about direct mapping. Okay, let us take some example here. So, suppose given that cache line 64 kilobyte, that means size of the block in the cache. Okay, no, this is the not size, cache what is called is cache, total cache size is 64 kilobyte and size of cache line, that is 4 bytes. That means block in the main cache memory size is only 4 bytes. As you know, the size of the cache line is same as the size of the main memory block. So, and then what is the main memory size? So, this is main memory size is 16 megabyte. Okay. So, this is 16 megabyte, this is 4 byte and this is 64 KB. Huh? This is KB. Now, question is how do you divide the main memory address if the direct mapping is used? How do you divide the address of main memory if direct mapping is used. Okay. So, then how many bit of address CPU should generate? That is nothing but the number of bits to represent the main memory, that is main memory size. So, main memory size is 16 into m 2 to the power 20, each location has 1 byte. So, this is nothing but 2 to the power 4 into 2 to the power 20 bytes. So, that means main memory address is 24 bits. So, therefore, this is total 24 bits. So, from here now you have to divide into 3, one is word, another is cache line. So, this is cache line, this is word and this is tag. Now, cache line, okay, word. How many words are there in a block? So, that is given by size of the cache line is 4 bytes. So, 4 bytes, to indicate 4 bytes, how many bits do you need? Only 2 bits. So, therefore, word will be 2. Now, cache line, how many cache lines are there? So, that you have to, so what is the size of the cache? That is 64 into 2 to the power 10 kilobyte, right. 64 means 2 to the power 6 and each cache line size is 4 bytes, that means 2 to the power 2. So, that will give you 2 to the power 14. So, to identify each cache line we need 14 bits. So, therefore, this will be 14. So, total is 24. So, this is 16. So, therefore, tag will be how much? Tag will be 8. So, that is the way we divide, we should divide the main memory address. Okay. One more example of let us say main memory is very simple example, main memory is only 32 bytes and cache size is 8 bytes and block is 4 bytes. How do you divide the same question main memory address? 32 bytes means 2 to the power 5 bytes. So, therefore, main memory is total 5 bits. That will be divided into 3 parts. What is that? Block size is 4 bytes. So, that means how many bits? For word is 2 bit. Now, cache size is 8 bytes, right. So, 8, so 2 to the power 3. So, 2 to the power 3 divided by 2 to the power 4. So, we have 2 cache line. So, this is the number of cache line. So, how many bits are required? So, you take log of 2. So, 1 bit either 0 or 1. So, therefore, this should be 1. So, therefore, tag will be 2 plus 1 3. So, tag will be 2. So, this will be cache line. Okay. So, in summary, for direct mapping what happened? Main memory address is divided into 3 parts. One is word, this is line, okay, and then this is tag. So, this one is S and let us say this is R. So, obviously, this will be S minus R and this is W. CPU generate this address. Then what we have? We have cache memory here, this is block or cache line. With each block there is should be a tag. So, okay. So, tag maybe we can write it here. Okay. Now, we have a big main memory here, it is having also block. Okay. Now, CPU generate the address. First, it will search into the cache memory. So, this is R. Okay. So, it will go to the particular, let us say this block. This is not sufficient, because it needs to check the tag also, and it should match whether this tag is same as tag available in that particular block. So, there should be a comparator that will compare with here, and this tag should be compare here. If it is matches, okay, then only we can say the data is available in the cache. If it is miss, then it is not available. So, if it hits, then what will do? So, it is already identified. So, if it is identified, so now this word should come here. So, which word it should access? So, it will go to that particular word here. Now, if it is miss, so entire this thing will come, that is S plus W, already W is there, it will identify this block. Okay. So, if this is the case, then what it will do? It should be available in the main memory. So, then it will go and then it will fetch this particular block and then word. So, this is pictorial representation for direct mapping. Now, this is good, but it has one major drawback. As you see one example here, let us say you want to add A plus B. A is located in the block 5 and B is located in the block 55 in the main memory. Interestingly, if you see that 05 and then 55 both will be mapped to the same location of the cache line, that is 5. Not only that, so 10 such block will be mapped to the single cache line, as we have seen earlier example. Problem is that, see, suppose first A will be referred, so it will be brought to the cache memory of block 5. Next it will go for B, again it will map to the 5. So, now 5 is no longer here, 55 came. Now, go for the addition, but another operand is not available. So, then again it has to be brought, but again 55 will go away. Even though there may be a cache memory here, there are spaces here, but because most at least 10 blocks of the main memory is mapped in a single location, if you need 2 of them at the same time, you will not get them, even though there are space in the cache memory. That means, space is there, but because of the direct scheme mechanism, we cannot keep both 5 and 55 together in the cache memory. So, therefore, every time, so whenever you need the data, that is 2 pages at the same time, so there will be always space fault here. Okay. So, therefore, there is another scheme is called the associative mapping. So, associative mapping basically removes this such kind of drawback. Okay. Why this is happening? Because we are keeping fixed place for a set of blocks. So, if we remove that restriction, what restriction? Now, blocks can be placed anywhere in the cache memory, then we can keep 5, 55 all together, because there is no space, then it is acceptable that you are sending data from the cache memory to main memory. But if there is a space and you cannot accommodate the block into in other cache line because of the problem in the mapping scheme. So, therefore, next part is something called the associative mapping. So, there is no restriction, whenever you need it, you bring the data and you put in the cache memory. Okay. So, therefore, in earlier case, so we had the word, we had the cache line and then tag. So, because we do not need to identify which cache line it is going, because it can be any place until unless it is becoming full. So, therefore, we remove this part here. So, in case of the associating mapping, what we need it? We need only the word and tag, and tag is exactly the block number. So, here 05 or 55. So, this should be block number 55 or 05. So, this is the associative mapping. Okay. So, let us talk in say example earlier case. Earlier case what happened? In case of the decimal example, we have 10 blocks here, okay, and then we had main memory of 100 blocks, this is 10 blocks. Now, I can keep anywhere in the cache memory. So, therefore, there is no need to identify which cache line it should go. So, directly we put a block into the cache line. So, therefore, here what will have happened, but obviously you need to identify whether data is coming from the which block in the main memory, that you need to identify always, right. 55, 45 or whatever that there are different number of blocks. So, all blocks needs to identify. Say suppose if I say 125 and 225, this is two different address, because this block number is different, it can be the same, what can be the same, but block number is different. So, therefore, in this example what we need to do? We need to identify the word within a block. So, you need only one, and then you need to identify the block, which block in the main memory it is coming. So, therefore, this is 2, total is 3 bits is required to identify, 3 digits is required to identify a particular word in this example. So, maybe we can take the similar example whatever we learned before, but do not consider that is how cache line is important, but we will go for different ways, we will see with one example here. Let us say we can take a simple example, this one here. Okay. So, main memory is 32 byte and cache size is 8 byte, block is 4 byte. So, if you use associative memory, how do you divide the main memory address? Okay. So, same example we can take it here, that main memory is 32 bytes. So, that main memory consists 5 bit address. Next, cache memory cache memory was 8 bytes. So, total size of the cache memory is it needs 3 bits, okay. And important is how many cache line. So, cache line cache size is 4 bytes. So, size of the block is 4 bytes. So, then the number of cache line is 2 only. So, then how many blocks? Number of blocks is what? 2 to the power 5 by 2 to the power 2. So, 2 to the power 3. So, 8 blocks in the main memory. So, there you divide this one into block size is 4 bytes. So, therefore, 2 and then 3 you have to identify the block number in the main memory. So, this is 3. So, this is work, this will work as a tag and this will work as a word in the in this example. Okay. So, we can go with one more example and then we will talk about the last mapping scheme, that is set associative mapping. Okay. So, maybe we can go in one, this is easy example, maybe we can go this example. Cache is 64 KB and size of the cache line is 4 byte, main memory size is 16 megabit, 16 megabytes. Okay. So, then total length is 24 as you can see, and then size of the cache line is 2. So, this remain 2, therefore, if you add 22 that will be the tag line. So, this is word and tag. So, for in this example say, so example number 2, here it was 64 MB. So, that means 2 to the power 6 into 2 to the power 6, right, 64 or 16. It was 16 MB. Okay. So, it was 16, yeah, no issue, you can work with 64 also. 16 MB, 16 MB means 2 to the power 3 into 2 to the power 20, 16 MB, right, yeah, 2 to the power 4 into 2 to the power 4. So, 2 to the power 24. So, number of total bit will be 24 here, and then what will be block size is, you can see block size is 4 bytes, right, block size is 4 bytes. So, that means 2. So, this will be 2. So, rest 22 will be the tag. So, now we will say diagram here. So, in similar diagram how it works is like, so CPU generate the address, main memory address, that will be divided into 2, word and tag. Okay. So, now what happened here, it generate the tag. So, in case of the cache memory, each block should contain a tag. This is tag, this is tag, this is tag, this is tag, this is tag. Okay. So, now what happened? This tag needs to be compared with the tag of the each block here. So, therefore, there should be a powerful comparator which basically compare the tag generated tag with the tag of Okay. So, all tags should be compare and it should be done parallel. So, there is a special circuit where this comparison will be done parallelly with this one with the all tag. If there is any place there is a match, so let us say it is matching here, that means that particular word is available here and then this word will be added this position. So, if this is hit, this will work here. If it is miss, then this entire part will come here. You have a big main memory. So, here it will work. So, here this is example of associative mapping. But this circuit, let us say here this circuit is very complex circuit which basically compare parallelly. See, suppose if you have a cache line of say 2 to the power 12. So, that is those many 2 to the power 12 cache line, then 2 to the power 12 tag needs to be compared parallelly and results should be fetched within few seconds. Okay. So, this require a complex circuit. So, therefore, in general neither direct mapping is used, neither associative mapping is used. So, now we will talk about set associative mapping. Set associative mapping. This is nothing but the addressing basically the drawback of direct mapping. What is the drawback of the direct mapping? Many of the blocks is mapped into a single block in the cache. So, that was removed in the associative mapping, but associative mapping problem is it needs the complex circuit. So, it removed the drawback of associative mapping. So, in this scheme first direct mapping is applied, and followed by associative mapping. Okay. So, what we do it in earlier example, if you see here what we had? We have the cache memory here, there are 10 blocks, we have 100 blocks here. What is done essentially? We have block already. We divide the blocks into, we group blocks into a number of set. Let us say this 5 will form set 0, another 5 will form set 1. Now, we apply direct mapping over the block of main memory, but earlier we are using the j modulo m, m is the size of the cache line. Instead of m, we will see how many sets are there. So, instead of s, we will use j modulo s, number of set. Now, once we identify the number of set here, say either set 0 or set 1, now within a set we apply the associative mapping. That means, within a set we can keep anywhere. First we apply direct mapping using set over main memory block, and once it is identified, now we will apply the associative mapping. That block can be placed anywhere within the set. So, that is why it is said ki set associative mapping. Okay. So, with that I stop here. In the next class we will talk in details associative mapping, and we will give few example in the next class also. So, I conclude today's class.